If we want to talk about the relative strengths of acids and bases, that's kind of a broad topic, so we'll just jump in and start giving specific examples. If I have what's considered a strong acid, because it's a strong electrolyte, it will produce essentially 100% in an aqueous solution. You will get hydronium ions. In an aqueous solution, a strong acid will 100% produce hydronium ions. There'll also be whatever anion is present based on what formula you have for your strong acid, but the H3O plus is the product when you have a strong acid, and for that reason we consider H3O plus to be the strongest acid possible, because any strong acid is going to essentially revert to H3O pluses in an aqueous solution. Likewise, any strong base is going to 100% produce hydroxide ions. For that reason, we say that OH minus is the strongest base possible in an aqueous solution, because any strong base is going to be hydroxide ions. So these are considered the strongest acid and the strongest base when you're talking about an aqueous solution. So, and we don't have to be talking about an aqueous solution to be using the Bronsted-Lowry definition, but in general chemistry, we almost always are in an aqueous solution. Next year, when you go on to organic chemistry, you'll do a lot of things that are not in an aqueous solution, and so you'll have other strong acids and strong bases in that case. But for us, for this semester, we're going to be in aqueous solutions, and so those are our strongest acids and bases, based on the fact that our strong acids and bases are essentially going to produce 100% of those. Now if we want to look at a conjugate acid-base reaction, and I'm just going to write a generic one, if A is my Bronsted-Lowry acid in this reaction, he has to have a hydrogen in order to donate it, and we'll call our Bronsted-Lowry base B. If this is in equilibrium with their conjugates, HA being the Bronsted-Lowry acid, will donate his proton to B, being the Bronsted-Lowry base, and so A will become A minus. He'll have a negative charge because he's giving away an H plus, and B will become BH with a plus charge because he's accepting an H plus. So this is the conjugate base of my Bronsted-Lowry acid. BH plus is my conjugate acid of my Bronsted-Lowry base. In this generic weak acid, weak base reaction, I have conjugate pairs. Whichever side of my reaction that has the stronger acid and base, that will be the side that will proceed farther to the other side. And that sounded a little weird. For example, if HA is a stronger acid than BH plus, this one would be the weaker acid. By stronger, what we mean is that it is more likely to produce BH plus than BH plus is likely to produce HA. So a stronger acid is one that provides a more forward reaction. If HA is my stronger acid in this example, what I will find is that B will be a stronger base than the A minus. So B will be stronger than the conjugate base on the other side. This will be the weaker base. I will always notice this sort of pattern if I start comparing strengths of the acids on either side and the bases on either side. In that case, what I find is that the reaction favors the weaker side, which means the reaction goes further toward the side where there is the weaker pair. In terms of the equilibrium of this reaction, we might say the equilibrium lies to the right. If my weaker pair are on the left, then I would say that the equilibrium lies to the left. So the reaction favors the weaker pair because the stronger pair are going to proceed with the reaction more so than the weaker pair. All right, the next thing we want to look at is we want to look at strengths, relative strengths of acids, and we're going to focus on acids for a while, looking at the periodic table.